We're going to talk today about joints and veins. So what are these? These are planar cracks with no or very small shear displacement. So yeah, these are pretty much any rock outcrop that you find will have the joints or veins. They're basically just cracks where there's very little, the things that were on either side of it. They're not faults, or there hasn't been much motion. So these are ubiquitous, means that they're all over the place. Ubiquitous in rocks. They often occur in parallel sets. And one more sort of bullet point here. The planar surface of a joint or a vein is often perpendicular to the least of the principal stresses. So if this is what the joint looks like, we can be pretty confident usually that's the sigma 3 direction. So causes. So several different causes. Contraction of an igneous body. During cooling. This forms what we call columnar jointing. And we'll see some pictures of these things. Another cause would be, this is probably the most common, release of pressure due to erosion. And finally, forces due to plate tectonics. Call these tectonic joints. And why do we care about these importance? So, for one thing, they facilitate weathering of rocks. So they're cracks, and so water will, rocks. Water will infiltrate along the joints, and that's where most the chemical reactions involved in the weathering process will occur, preferentially. So there are also, other geologic fluids will also move along joints. So they provide conduits for mineral deposition. And so when we start talking about depositing minerals, we call them veins in this case. So a joint is just a crack, and if it fills in with something, we call it a vein. And they influence the strength of rocks. So this has a lot of sort of engineering type applications or importances. A small sample of a rock may have some qualities, but when you look at the larger scale hillside, if it almost inevitably does have a bunch of these joints in it and cracks, then it's going to be a lot less strong than the sort of in the areas that aren't. So next we'll look at a bunch of slides of joints and veins. These are some slides now of joints and veins. What we're looking at here is a series of in this case, veins and some joints. Okay, so the veins shown here are these sort of parallel yellow reddish stained features. So these are cracks that have filled in with some minerals, some having some iron which oxidized, giving it the reddish color. But you also see here just these like a parallel crack here, a straight crack. Likely the horizontal here is the bedding surface. I'm not completely sure about this, but yeah. So oftentimes, like a joint can be mistaken for a crack. So some features about joints: they're generally planar, continuous. They can go for quite a long ways. They cut through. Going means they cut through. Often cut through different rock layers. They occur in parallel sets. They usually have very small offsets. And they're generally results from tensile failure. So the rock being pulled apart or very small amounts of shear. And yeah, joints may contain veins. So sometimes you'll see a set of these cracks that have vein material in them. Here's an example from upstate New York. So here again we have a horizontal bedding, and you can also see that there's, at 90 degrees to that, there's some planar surfaces. So there's one here in the distance, a little bit underneath the bridge there, going up right along here, and in the creek. So these are classic examples of joints. Igneous bodies will also, so joints, as we said, they occur due to contraction during cooling, and this can happen, to a magnificent extent in igneous bodies. So this is these are called columnar joints. This was basically the inside of a volcano, the lava in there that had cooled, and when it cooled, it shrinks, and they form these columns. Here's another example of some sedimentary layering, which is more or less horizontal here, as well as some joints. It's broken along these kind of planar surfaces. You can see here this one continues down, this one a little bit as well. There's one coming down here, several here. So I think you can even see them in the distance here along this cliff. These vertical parallel cracks, semi-parallel. This is an example from the southwestern U.S. Again, we have relatively horizontal sedimentary layers, a sandstone here forming a cliff, more erodible, muddier rocks below. And these features have formed basically, the joints in this rock were running along this face and on the other side. So you just get left with these sheets of rock balanced. I mentioned that joints are important for economic geology. So in this case, you can see a network of joints and that there's been some mineralization, some change in the composition of the rock along them, where the rock has turned a yellowish color. And that, so the cracks there allow geologic fluids to flow through the rocks. In some cases, if the joints are opening at the same time as the flow of the fluid, there's like a drop in pressure happening, and that can facilitate the minerals that are suspended in the water to come out of the water and deposit. They're also important for stability. So this is an example of, this rock looks, probably, the parts that aren't affected by jointing are very strong, but because it's cut through in all different orientations with joints, they have to put up the safety net. So this is most outcrops of rock are filled with joints. So it's really more the properties of these joints that control the strength of a large body of rocks than the internal properties themselves. And this is important for mining, for construction of roads, dams, all sorts of any projects that involve moving large amounts of rocks. There's a key for scale. This is an image. So joints will often have some we're looking at the joint surface here, down on it. So the joint is parallel to the screen. And it's not uncommon to see some kind of cool radial textures. Some different examples. Here's some cross-bedded sandstone. You can see the sand layers dipping off to the right here, and then we see some more dipping off to the left. And this is a giant joint surface. So we can learn a little bit about the formation of joints from this. They will radiate out from the center. So the sort of the center of the circle, kind of like tree rings. The joint would have formed there and gone off in these directions. And then you can see like there were some subsequent little joints happening as well. Here's another example, sort of a radiation point here, and you can see this texture kind of going off in different directions. Here's another sort of locus. And so what these show is they show propagation of the joint from the left to the right here, as you can sort of trace these lines migrating off the center axis, and we'll see in a second here a diagram explaining this a little better. So joints can be non-planar. So there's little topography. What we've been looking at are sort of a topography on the joint surface. We call them plumose structures when they kind of have this feather-like aspect. And again, this one propagated from the left and towards the right. There's a nomenclature, as you can see, for these. Not going to worry about that in this class. but just know that these features have been described and studied in quite a bit of detail. And the most interesting thing for our purposes about them is we can sort of learn about the way the fractures are forming by looking at them. So a joint could occur by just pulling apart. That's going to have this sort of plumose structure. The same surface a joint could form by a different mechanism, of sort of a twisting mechanism here, and that's going to have the joint rating for the bottom. So these can give you clues to the stress environment involved in the formation of the joints. So joints can occur during. Well, joints are going to occur due to some change in the stress condition, basically. This could be during burial. One example we showed earlier, actually, in class during the discussion of stress and the effect of fluids. So if the fluid pressure here is high, shown as PF, this can occur during, as sediments are accumulating, they're increasing the pressures on the rocks below, and that can cause fracturing, jointing. So these words are synonyms, and these are often limited to a single bed. Most joints that we see occur during uplift. So, and the reason for this is that there's more than one reason, but basically rocks as erosion is occurring, rocks are moving towards the surface of the earth. And so the rock is both cooling down, which causes it to shrink a little bit. The rock is also being unloaded, so the weight of the rocks above is decreasing, but the pressure of the rocks around them is not necessarily decreasing at the same amount. So the rock is experiencing this change in the principal stresses it's experiencing, and that will inevitably cause some shrinking as the rock nears the surface. And so that's an elastic strain that's relieved by the formation of these fractures. And the systematic orientations of joints, as we said, they tend to occur in parallel sets, can give us a sense, of the strain that is occurring. That the joints are facilitating a very small amount of strain. So we can look at the orientations to get some idea of the S1, S2, S3. And those offsets can be used to estimate a total elastic strain that's relieved. So this shows a sort of a little kind of diagram of that. We have some rock. It's moving towards the Earth's surface. As it's going towards the surface, it's actually there may be a small amount of increased surface area, basically. So that's indicated by the kind of wedge shape of this. As the rock goes up, it is sort of being asked to expand, but it can't really accommodate that. That results in the least principal stress being horizontal during erosion or exhumation, as we call it. And so in a map view, if you see a series of joints, you can assume that that sigma 3, the least principal stress, is oriented perpendicular to them. I should clarify, I just mentioned exhumation and erosion. So just to be clear, erosion is, wind, water, removing the upper most layers of the Earth's surface. But you can also bring rocks to that will bring rocks to the surface. You can also bring rocks to the surface along faults. So a broader term, exhumation, means the combination of erosion and sort of faulting that brings rocks from deeper levels towards the surface. So this here we see the south of England and some of France. And what's shown on the map here are the orientations of joints. So these joints are often consistently oriented over very large distances. This is a 100-kilometer scale bar. Joints can occur as single sets, as these are the thin lines here. Or they might appear also as in sort of conjugate sets that are like consistently oriented, but not in sort of pairs of orientations. And so you can see here, these are vertical joints, steeply inclined, so not quite vertical. They have a dip. You can see the little strike and dip symbols being used. So these are all of them kind of showing this northwest, southeast fracturing. And what's also shown on here is, so we don't know exactly when that fracturing occurred. We just observe those joints. But if we look at what are called, there's two other things we can look at. One of them is related to earthquakes, which can tell us an idea of a stress direction. These are shown as the big arrows. And the other one is borehole elongation. So when they drill, when drill holes are made for various purposes, water wells, oil wells, they will often collapse or fracture. And so that gives us an idea of the stress directions that are currently being experienced. And so this is the elongation direction. So you can see that these are perpendicular to the extension to the joints, and that's what we'd expect if the current stress environment is the same as the environment when the joints formed. So that looks to be the case in southern England and continues on into France. So you can, for these boreholes, you can kind of think about, imagine a circle, and the arrows are showing that that is being pulled apart. If we were to draw the strain ellipse, it would be a northeast, southwest strain ellipse, which is same thing you would construct looking at the joints. This is this is a geologic compass for scale. We're seeing multiple sets of joints here. So there's a set kind of running along like this. There's another set at about 90 degrees to that, and there's some complications in there as well. These are what we call, you can sort of see little parallel joints at an angle to the darker ones there. So just to review, joints facilitate weathering of rock. They influence the movement of geologic fluids, including groundwater. They provide sites of mineral deposition, and they can influence the strength of rocks. They can also tell us some other additional information about the strain that's occurring. So what's shown here are some diagrams of veins. So in this case, it's the fracture is filled with some material, and often what happens is that as there'll be a crack, and it will fill in, and then there'll be another, it'll re-crack. So here we've got probably 1, 2, 3, 4, 5, 6 episodes of cracking. And little bits of the wall rock will become incorporated in those veins, and so you can sort of see this record of opening. And based on how these line up, you can see the direction of opening. So we have what we call extension veins, where basically it's just opening mainly. Down at the bottom, we have shear veins, where the motion is parallel to the boundaries. And then there's intermediate possibilities as well. So this sort of activity can actually give us information about the sense of shear, the movement of, what the direction of movement. So study this for a second. These are basically like the releasing bends of a strike-slip fault. So if you find joint material, but you know that was an opening that occurred, and you see that some areas like this, there was no opening. So you can explain this if you take this upper block and move it to the right. We call these jogs, where the fracture moves over. So here's an example, and just take a moment, maybe pause the slideshow just to think about, okay, is this right lateral or left lateral motion? In this case, the vein material is this black material. So as was shown in the previous slide, this area where I'm hovering the mouse used to be connected to this area where I'm hovering the mouse. And by motion along this, shearing along this fracture and this fracture here, if the upper block moves to the left, you'll open up this space. And as I mentioned before, you can take a piece of paper, cut it straight up, make a jog, cut it straight again, and you can demonstrate this yourself.